मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, my dear students, now we are going to discuss the third lecture in the series of rolling processes. So far we discussed under the technology of metal forming the previous two lectures covering the in general the rolling processes, the flat rolling, shape rolling and other rolling processes, thread rolling and all those things we discuss. Alright. So, in this lecture, because the process is now clear, the role of rolling is clear, the products, the what kind of products we are going to deliver with the help of rolling process is also very clear. And the order of mechanical properties, the surface finish, all those things, tolerances achievable, that we have already seen it. Now let us discuss the basic mechanics of the rolling and the related issues, means how do you calculate power, how do you calculate torque, and then how do you select a motor so that you must have a proper machines for rolling depending on the stock you want to start with. See the different alloys we come across in order their hardness, in order of their the yield strength, in order of their toughness. It requires a different varieties, different ways for producing the products by way of rolling, different way of rolling. So we would discuss especially the mechanics part, and let us see how we develop some simple formulation that can be used for most of the rolling processes. See the two broad category we have already seen, cold working and hot working. Warm working is also popular, which is in between the two. The cold working, when we say, we most often come across the situation like these various rolling processes. As I said, most of the rolling processes start with plates, right? And I said when the thickness after you start with blooms, the plate, if the thickness is more than 6 mm, as yesterday we explained, we say it all plates when the thickness is more than 6 mm. And when the thickness is less than 6 mm, this category would be called as sheets, right? So look at this figure here. You know that the initial the ingots, that has the cast ingots, and you convert into blooms and billets, and you do it by rolling process. Bloom is the product of the first breakdown of the ingot, where the cross sectional area is around 36 inches square, whereas the billet has a cross sectional typically around 1.5 inch to 1.5 inch. The slab is a hot rolled ingot. In fact, when you start with the slab, it's a hot rolled ingot of width about twice the thickness and of the area around 16 inches square, right? And the cold rolling produces sheets, strips and foils with good surface finish. This we discussed yesterday, right? Now you see the three roots of this. When you start with the first one, you start with slab, and then the hot strip you produce, and after hot strip you can pickling and oiling and that, and then you can produce out of the hot strip coils, you can produce the cold strips. This we discussed study. And from the slab itself you can start with the scalp, and then we also discussed to produce the welded pipes, seamless pipes study. So that's another route. All right. The third route, that you start with slab and you convert with plates, and then this plate is further reduced to steel plates of smaller thickness. Okay. So these are the three routes. Now the next route, when you start with the billet, right? So billet, as I said, has got section around 1.5 inch to 1.5 inch, and when you start with, so first you can hot roll to bar, as you see here. The rolling, the rollers here you have of different groups on the same roller. You pass through the billet starting from the one group, and then the second side to the other group, third group, and thus you can get reduced by the hot rolling bar. And then after hot rolling bar you can further reduce it for finer rolling by cold drawn bars also. You can dry it again. The second route out of the billet could be your rods. When you produce with the rod, and then these rod can further be reduced in diameter like wires, so you can use wire drying products, right? The third route, when that you start with billet, it may be your tubes, as I said, the spun seamless tubes, and then you can start with round tubes, and then you can further reduce by mandrel, way of mandrel between, and there is a two roller and there is a mandrel in between, so you further reduce the diameter, and you are able to produce seamless pipes. So these are the some products. On the other hand, if you start directly with blooms, right, so you can go for structural shapes. So as I said yesterday, the structural shape, variety of structural shape, S shape, L shape, I shape, rail shapes, all that can be produced with the help of arrangements of the roller in horizontal fashion and vertical fashion, as you see, and then many other varieties. And here initially in the few passes, as I said, you have the roughing passes, and then intermediate passes, and then rolling the finishing passes you go for. Initially you may have a hot blooms, and then finally for the finish pass you may go as the very little temperature, and sometimes you may be cold as well. So starting with these basics, repeating the last lecture almost, let us start the mechanics of rolling now. So look at this figure, right? So again you have, it's a two high rolling mill. So if you look at this one, what you have two rollers, right? And the rollers diameters are R, the two rollers, and initial thickness, suppose you take as the H, all right, and it is reduced to height H, final HF. The initial pulling velocity is V0, and afterward it comes out from point C, that is from point neutral point capital N, it is the velocity Vf. So you can note down the strain, that is the true strain, which is the natural log of h by h0, right? So width of the sheet, if it is taken as small w, and that means this is this does not change with deformation width, it is assumed. Okay, so conservation of the volume, if you look at, that's the volume constancy equation. So that means V0 H0 and W must be equal to Vf H and W. Okay, since Hf is less than H0 and since W remains constant, so Vf is larger than V0. That's very true. In addition, Vr, which is the roll surface speed, if you take the roll surface speed Vr, right, so is larger than the workpiece to the left of a point capital N, that is the neutral point, and Vr is lower than the workpiece to the right of the neutral point. That's the things to be remembered again. And the contact angle is alpha, which is shown here, the total contact angle of the workpiece between the rollers, right? So you now mark the delta H, because delta H is spread on both sides, so delta H by 2 is the from, you can see that the vertical height from E to D projected to the vertical line. So starting with this, if you look at to the left of E, that is the neutral point, because the Vr is greater than V0, so the frictional stress on the workpiece is directed anti-clockwise, as you can see, and conversely to the right of N, that is the neutral point, we have Vr is less than Vf, and so the frictional force are directed clockwise as shown there. So neutral point, the N is in fact a neutral point. So at the neutral point there is no relative motion, and the frictional force therefore must be 0. Okay. So let us start with the analysis now. So what we are going to have, there are certain assumptions that we are going to analyze this problem under plane strain condition, right? Plane strain condition. Secondly, the constant magnitude of friction coefficient all around the surface in contact between the workpiece and the rollers is assumed. Thirdly, the constant circular arc of contact is assumed, because sometimes the arc when the roller deforms, so the arc of contact would be disturbed. So it is assumed that the circular arc of contact remains same. And fourthly, the neutral point within the arc of contact, it remains within, it does not go out, right? So this is also a very important point to start with. And fifth, which is very important, there is no elastic deformation. So even if it is there, let us neglect it. It is very small amount of the elastic deformation as compared to the plastic deformation of the workpiece. So we can neglect it. So assuming these 5 points as such explained, let us start with the slab approximation, right? So looking into this, one can look upon the workpiece in contact like here. So you can see the point E and you can see the point D there. So plane strain compression of this piece, because W, that is the width, does not change. So we can say it is a plane strain compression of the piece. Okay, this particular piece which is marked as red. All right. So if you use the slab approximation, which is similar to forging with friction, right? So looking into this geometry where the forces F and the frictional forces are there, the length L is the length of contact, S and delta H by 2. If you look at this portion which is blue shown, so that corresponds to the friction hill, and it is very similar to the forging we discussed, right? So L is what, you know, if you see into the geometry, that is the triangle, so L square is equal to S square plus delta H by 2 whole square, and then you can derive the L which is equal to R delta H, alright. And then you can, as you recall previously, you can have the pressure, average pressure as Y1 plus nu A by H, when this is taken as 2A, similar to forging, and A is L by 2, there H is H0 plus HF by 2, F is your P average LW, okay. So this is quite similar to the forging one. Please note that rolling is the process where there is a forging as well as drying, right? So more accurately then one can say that at the entry zone now we can take a slab, and at the exit zone we can take a slab. So that's from the neutral point. From the neutral point, before that it is the entry zone. From the neutral point after that it is a exit zone. So if we take the element and let us see the equilibrium of this element and the forces acting on that, this is what is shown, these element at the entry zone and exit zone. You can see the direction of frictional force before within the entry zone, and the direction of frictional force opposes in the exit zone, and the stresses, that is sigma x plus d sigma x, and the other side is d sigma x, and all these geometry. So we can now see this, the entry zone. Let us see. So we have entry zone. So all the forces, if you see the balance, the force equilibrium, so all the forces in x direction must be 0, and therefore this implies that sigma x plus d sigma x and multiplied by h plus dh minus 2p r d phi, alright, sin phi minus sigma x h plus minus twice nu p r d phi cos phi is 0, okay. Phi is the angle that has been the inclination angle which is shown there, and this equation is for entry as well as exit. So phi becomes alpha at the entry, you remember there. So phi is nothing but alpha at the entry, and assuming that the plane strain compression and yielding, therefore the effective stress can be equal to the yield stress, and that leads to P minus sigma x is equal to y, that is the yield stress of the material, okay. Is this clear up to this? So any stage you have any problem, you can ask me. You raise your hand and let me explain it again, okay. So then if you solve this equation, the equilibrium equation, and if you apply the boundary condition, and if you apply the Tresca-Yield criteria, as I said, so if you incorporate, that is what's the Tresca-Yield criteria, so you can now find out the P, that is the pressure at the entry zone, as here, and that is y h by h0 e raised to the power nu capital H0 by h. This is at entry zone, and P at the exit zone is also given there. So out of that you can now calculate the capital H and H0, which is shown there, and then the neutral point, the angle at the neutral point you can find out, which is under root hf by r, 10 of under root hf by r and capital Hn by 2, and therefore the location of the neutral point, that is phi n, and Hn, the neutral point, the height capital H corresponds to half of h0 minus 1 by nu natural log of h0 by hf. Some of the steps I have left for you, please do it yourself. So if you look at now, if you draw this using these equations P and all these here, so if you draw the values of the P by Y, it's in non-dimensional term, so you can now distribute the pressure in the roll gap as a function of the coefficient of friction. Alright, so note that as the friction increases, the neutral point shifts towards the entry, right? Without friction, when there is no friction, the roll slip and the neutral point shifts completely to the exit side, right? So if you look at this one, the rolling direction is on this side, and the entry side phi is alpha and exit side phi is 0. So when you draw it, you see according to the different friction conditions, right? When the friction, so you can see the P by Y value, and that's the neutral point phi n is showing. So phi n is 0 at the exit, and at the entry it is phi n at alpha. Okay, the phi is alpha at the entry. The value starts from 1 to around 4.2, 4.3, and as the friction increases, you can see the value higher P by yield stress, and as the friction is less, so when the friction is almost 0, then you can have a different kind of line. So this is a asymmetric friction hill, right? So asymmetric because smaller the friction coefficient, the smaller the value of phi n you observe. So once you have calculated the pressure required for the deformation, one can also calculate the torque and power as the usual way. So what is torque? You know, if you see the free body of the roll, the torque is a rotational manner. So if you look at the force which is coming up of the roll force, that is the vertically being applied, and the friction, and it is on the, you can look at the T applied, so the free body one, so if you look at that particular portion, the P average is what we have already calculated, A, H and those. So if we assume that the neutral vertical force act through the middle of the L by 2, if it is, then W is the length of the workpiece, right? So the power can be calculated as like the T multiplied by 2 pi n divided by 60, right? Where n is the revolution per minute of the roller. Alright. So sum of this torque would be equal. That means this implies that the T applied must be equal to F multiplied by L by 2. Okay, where capital is L is your under root R delta H explained earlier. Alright. So you can now calculate the T applied, which is equal to F multiplied by L by 2. Okay. Out of this, effective yield stress in the work hardening material. If it is, see, if the material is not hardened, work hardening, then the situation is different. But most of the time, in cold working especially, the material gets hardened, and therefore, like you see in the forging, rolling, extrusion operations, etc., when the material has work hardening, then one can use an average Y value, that is the yield stress, that represents the total strain imposed on the material. All right. So if you look at this stress strain curve, so the average is defined somewhere here, and the strain is experienced by the workpiece would be equal to the ln h0 by hf. So if that V average is taken, the work done can be calculated. All right. So work done, if it is calculated, then that would be the volume multiplied by integral sigma and d epsilon, right? And this integral must run from 0 to the strain, and if you further calculate it, that is what is calculated, and that results into volume multiplied by V average multiplied by strain, or simply the V average is calculated as K epsilon n divided by n plus 1, and this equation what I gave it in even in the first lecture of the rolling. So that is how it is derived, very simple. Please note that the speed with which the rolling takes place, that is very sensitive. If the material is very sensitive to strain rate, so the situation becomes much more difficult, and modeling those situations so that there is no defect form, one has to be very careful for selecting a proper strain rate in the rolling. You know the strain which is epsilon, this is nothing but the natural log h0 by hf, and if you calculate the time, so time can be calculated as capital L by Vr, where Vr is nothing but the 2 pi nr by 60, where the surface velocity of the roll, and Vr is the surface velocity of the roll, and n is the revolution per minute rpm. Okay, and therefore the strain rate can be calculated as what? L by Vr natural log by h by hf. So this is the simple formula for calculating the strain rate in rolling. The strain rate is important since ductility and flow stress of the material both depends on the strain rate, right? Typically one must select an appropriate window of strain and strain rate per pass, so that the highest production rate can be maintained without creating unwanted microstructures or defects and cracks in the material, right? So that's how I said, if the strain and strain rate is not proper, lot of problems related to the microstructure, defects, cracks will develop. So there is a balance between the strain and strain rate, so that you do not come across any problem as far as the microstructure is, the grain boundaries related issues, defects, all kind of the defects I discussed, and the cracks, edge cracking and center line cracking, so all those you do not come across. So that's the, and therefore there is a maximum possible draft. See, for any rolling process, it is not like that anything you are going to deform, any thickness. So there is limitation. There is a limitation that depends on the roll diameter and the angle of contact as well as the surface finish. So the maximum possible draft, that we say the draft means h0 minus hf. So it can be shown that this h0 minus hf is almost equal to 2r multiplied by 1 minus cos alpha, and that is almost equal to r alpha square when the alpha is small. So the maximum value of alpha is limited by the friction, as I said. Okay, it is limited by the friction coefficient, and that is alpha max is around nu. You can go at least this alpha max equal to nu, and therefore h0 minus hf, that is the maximum possible draft, would be delta h, and that is nothing but nu square r, and that I explained quite earlier. In fact, in hot rolling, the friction coefficient is very high, is of the order of around 0.2 to 0.7, and even because of this, the sticking conditions are obtained and the material starts sticking. Hence the large thickness reductions are possible during hot rolling process, right, which is not possible in cold rolling. Basically, thin sheets are most often rolled using cold rolling. You know, the value of r, that is the radius of the roll, is kept low to reduce load requirements, therefore, in cold rolling. Usually the frictional coefficient nu typically varies between 0.02 to 0.3 only in cold rolling, and thus the maximum draft is possible, which is more important during cold working. Alright, so that's a little bit about some issues. As you know, when in usual manner, when you load the stock, so stock is in the coil form most of the time. So this the coil sheet are it is unworn, and it is now if you load it onto the line, you have back, front and back tension. So the coil initial stock and the final, where you after rolling it is again coiler is there. So that also gives a back tension. So back tension and front tension, let us see what happens. So if you look at this figure, so where the sigma b is the back tension, you got, and front tension is sigma f. Alright, so front and back tension are applied to reduce the load for rolling. Alright, particularly important during cold rolling process. It is very important, and it can be shown that at the entry zone, the P, which is the pressure we calculated, which is y minus sigma b multiplied by h by h0 e raised to the power nu capital H by h0, h0 minus h, and at the exit zone, the P becomes y minus sigma f, that is the front tension, and h by hf, and e raised to the power nu h. So the tension moved the neutral point to the right by sigma b and to the left by sigma f. You can see, because the minus term. Is this okay? And that's how it is going to help you, and it reduces the load for the rolling, especially in cold rolling, therefore. And that's how the use of back tension and front tension is significance here. Okay, so as I said, the rolls are under very high pressure, and there is a force, vertical force, roll force, that we call, and because of that the rolls may bend, and therefore we provide, most of the design provides a cambering of roll. So this what shows the cambering. So if it is properly cambered, so you get a, after, in spite of the heavy load, it may be you get the proper size, and This is what the figure A and B shows the use of camber, and it shows how the seat is going to be produced. If you produce more camber, then it is also not good, and there is a sufficient camber must be there so that you get a straight seats to be rolled. All right, because of the improper camber, as I said, and because of the bending, there may be many problems appear, like you see the wrinkles, you see the middle tear, and then because the edges has got compressive stress, and the middle line experiences a tensile stress, and therefore as a crack is formed. That is the edge crack we have already discussed. So cambering becomes a very important issue that is to be provided on the rollers to take care so that this defect does not appear. All right. So here this is what shows the waviness at the edges, which is often caused by breaking of rolls, the bending of rolls, such that the edge regions are thinner and the longer. So look at here. So that's the rolling direction, and that's the edge. Okay. Other defect arises because of the bending of the rolls, that is edge cracking, which is caused by low ductility, and in the center region the sigma y is 0 and mod sigma x is around sigma z, and at the edges sigma y is quite high, and so the sigma x becomes less than sigma z, and hence a tension stress is generated at the edges, and to make the length at the edges equal to that at the center, this causes edge cracking, and especially if the ductility is low, this problem arises. And another problem that we call it as alligatoring occurs by a complex process and added by defects in the original casting, like here. So if you see the tension and compression, and therefore from the middle, the shear, it will get sheared from the middle one. So, and that happens because of the improper casting, the original casting, right? So the effect of, if you provide proper camber, this effect can be reduced. But if the camber is oversized, that means this is what slide shows the possible effect when the rolls are over cambered, right? So now you see in this case, there are 4 cases where you have the first, this may be the mark, that is the rolling marks are produced. Second case, when it is over cambered and it is not properly distributed, this camber, it may totally shear from the middle, like there. It may cause the edge cracking, and it may cause the middle crack also because of the stresses and strain developed, tensile and compressive stresses developed, right? So that's how a proper camber is very, very important. If you look at a usual cross section of the rolling, usually you see the stresses that develop on the various cross section of the seat, because the seat is quite width, it has a width. So if I take some section from the middle portion, if I say take some section from the side, that is edge sides, and let us see the stresses that we have. So here in this slide there are 2 such sections. So at the edge side section, if you see the in the longitudinal direction, you have tensile stress, and on the vertical direction you have compressive stress. So this element is subjected to in the edge side, right? Now you see the middle region. So the middle region is different story. So the top side it is a compressive, but the side one it is again compressive. All right, because the edge side you don't have any compressive stress, and that is how usually the sheet develop at the edge side a compressive stress and the center side a tensile stress, and that is how the cracks develop, because it has to adjust itself with respect to the two regions, and that is how the residual stresses also develop. So smaller rollers usually tend to work the metal at the surface, okay, if the rollers are smaller. The metal extends on the surface, because as the material comes out of the rolls, the central bulk region puts the extended surface in compression, and this is similar to what occurs during the short peening operation, remember, okay. So the large diameter rolls, if you use large diameter rolls that often used in hot rolling processes, it tends to work the central region more than the bulk region, right? And this is because of the higher friction at the surfaces, and consequently the material is larger in the bulk than the surface, okay, and a tension stress is generated in the surface therefore, okay. So this is what's the because of these residual stresses are developed, and one has to take care that residual stresses does not develop of the order which is beyond the control, because that may lead to these all different kinds of defects. The defects control measures are very important in rolling mills. If you do not control it properly, and that's how there are online monitoring systems involved, along with online gauging system, and the gauging systems at the edge side, at the middle side, and nowadays laser operated gauging is also online laser operated gauging systems are there, and the moment there is any defect or any mishappening is going to happen, one can notice immediately and corrective action is taken. So that's how these are some of the issues that I wanted to share with you all, the students, and hopefully we would now, because we have so far covered the basics of rolling processes, varieties of rolling processes, mechanics part, defects, and the safe rolling. So there are certain alloys that are very common for we would take one more lecture to discuss here, and then the very important issue is the roll pass design, and especially the group design. What are the considerations to be taken for a good roll pass design, right? So we would discuss these issues in the next lecture, and I would like to thank you for your patience, for keeping silent, and question answer you raised, we discussed, and hopefully, because it's a web based course, so I need your feedback so that we can put more for you, and I thank you once again.